All the diodes you studied in previous videos were general-purpose diodes. There are several other types of diodes which are used for specific applications. In this chapter, you will get familiar with these types of diodes. The schematic symbol for the Zener diode is shown on the screen. As you see, the line at the end of the arrow in the diode symbol looks like the letter Z. In the first part of this course, which was about semiconductors, I mentioned that junction breakdowns should be avoided in normal applications. However, there are specifically designed elements that are designed to operate in the breakdown region. The Zener diode is a silicon PN junction that is operated in the reverse breakdown region. The IV characteristics of a Zener diode is shown in this graph. The forward region is identical to the simple diode. Since the Zener diode is operated only in the reverse bias region, I will focus on its characteristics in this region only. If the reverse voltage is increased from 0, the reverse current, which is indicated by IZ, remains negligibly small until it reaches the knee of the curve. This point is indicated by letter K, and the current corresponding to this point is indicated by IZ min or IZK. The current corresponding to the knee point is the minimum current that a Zener diode must carry to operate in the reverse breakdown region. At this point, the effect of breakdown process begins. The nominal Zener breakdown voltage is specified as Vz, and the current corresponding to this voltage is indicated by IZT or Zener test current. These values are available in the datasheet of a Zener diode. Zener diodes are available with different Zener voltages. The Zener voltage is set during manufacturing process by controlling the doping concentration. The maximum current a Zener diode can carry safely is called Zener maximum current. It is indicated with IZ max or IZM. In practical circuits, we have to limit the Zener current between IZ min and IZ max, so we usually use a current limiting resistor in series with the Zener diode. As you see on the graph, in the breakdown region, the current IZ may change from IZ min to IZ max, but the voltage remains nearly constant. Therefore, the ideal Zener diode is indicated by a battery having the voltage Vz. Practically, the reverse IV characteristics of a Zener diode is not ideally vertical. So the difference of Zener voltages between 2 points in the breakdown region over the change in the values of Zener current at the corresponding points gives us the value for Zener resistance. This is also called dynamic resistance or AC resistance. So the more practical model for Zener diode is equivalent to a battery with voltage Vz in series with a Zener resistance Rz. The power dissipated by the Zener diode is computed by using this relation. The maximum power dissipation is calculated by multiplying the nominal Zener voltage and IZ max, which is the maximum Zener current. Zener voltage changes for every degree centigrade change in temperature. This is called temperature coefficient, which is usually expressed in millivolts per degree centigrade. Temperature coefficient is expressed mathematically by this relation. In this relation, T1 is the final temperature and T0 is the temperature at which Zener voltage or Vz is specified. It is usually 25 degrees centigrade. Delta Vz is the change of the Zener voltage due to temperature variation. As an example, I want to find the temperature coefficient of a 5.1 volts Zener diode if the Zener voltage drops to 4.9 volts at a temperature of 80 degrees centigrade. The nominal Zener voltage is measured in 25 degrees centigrade. By using this information, the change in Zener voltage is minus 0.2 volts and the change of temperature is 55 degrees centigrade. So the temperature coefficient of the Zener diode is calculated as minus 0.071%. The analysis of circuits containing Zener diodes are quite similar to the analysis of ordinary diodes in previous chapter. You only have to keep in mind that in most applications, Zener diodes are operated in the reverse biased mode. So if this graph is the IV characteristics of the Zener diode, to analyze a circuit containing Zener diodes, we have to first calculate the voltage across the Zener diode. To calculate the voltage across the Zener diode, imagine the diode is not available and calculate the voltage across it. If the reverse voltage across the diode is greater than the Zener voltage, then the diode is operating in the breakdown region. So you can replace it with the ideal model, which is a voltage source that is equal to the Zener voltage. Or you can replace it with a voltage source in series with Zener resistance, depending on the required accuracy for your model. If the reverse voltage is between Vz and V gamma, then a very small current passes through the diode, so the diode can be considered as an open circuit. And if the voltage across the diode is greater than V gamma, then it will act as an ordinary diode in the forward bias region. So the complete model for Zener diode will be like this. And since Zener diodes are used in the breakdown region, I only focus on this region and simplify the model to this one. Imagine the Zener diode in this circuit is having the Zener voltage of 5.6 volts. If the Zener diode has maximum power dissipation of 170 milliwatts, calculate the voltage VL across the load, the voltage VR across the source resistor, and the current passing through the Zener diode. How much power is dissipated in Zener diode? Can we use a 170 milliwatt Zener for this circuit? First, I assume the Zener diode is not available in the circuit and calculate the voltage across its terminals. So by using a simple voltage divider, the voltage across the Zener diode is calculated as 8 volts. This is the reverse voltage across the Zener diode, and since it is greater than the Zener voltage, which is 5.6 volts, the diode is on or in the breakdown region, and I can replace the diode with its ideal model, which is a voltage source having the value of 5.6 volts. So the voltage VL across the load will be 5.6 volts and the current of the load will be 15.6 milliamps. The voltage across the source resistor is 12 volts minus 5.6 volts, which is equal to 6.4 volts, and the current passing through the source resistor R is 35.6 milliamps. To find the current passing through the Zener diode, I can write KCL at this node. The current passing through the diode is found to be 20 milliamps. By using this current, I would be able to calculate the power dissipated in Zener diode, which is 112 milliwatts. And since this power is less than the maximum allowable power dissipation of 170 milliwatts, we can safely use this diode in the circuit. What if the load resistor is a 91 ohm resistor instead of 360 ohms? In this case, if I remove the Zener diode and calculate the voltage across the diode, I will notice that the reverse voltage across the Zener diode is approximately 4 volts, which is smaller than the Zener voltage. So there will be a very small current passing through the diode, and practically I can replace the Zener diode with an open circuit. Therefore, the Zener current will be 0 and the power dissipated in Zener diode will be 0 as well. Since the diode is replaced with an open circuit, the two resistors are in series with each other, and the load current is equal to the current of the source resistor. The voltage drop across the load resistance will be approximately 4 volts, and therefore the voltage drop across the source resistance is approximately 8 volts. In the next video, I will show you how to design your load resistance so that the Zener diode always remain in the breakdown region. Also, you will learn how to calculate the range of the input voltage that will maintain your Zener diode in the breakdown region.